Hello, this is going to be a three-part video. Part one, I'm going to make a formal request for every science-y type person to really scrutinize this and to give me feedback. Well, actually not just me, but for the final experiment, because that's what part two is going to be for. Part two is going to address some of the things that flat earthers have said concerning why they should be seeing a 24-hour sun in Antarctica, when for years they said there was no 24-hour sun in Antarctica. And then, of course, because of this second point, I thought that I was going to also offer up some more suggestions for Will Duffy and the final experiment, which would be part three. First, I would like to make an announcement. I got myself a new toy. Oh. Yes, that is right. I finally decided I was going to spend the bucks and get myself a Blue Yeti studio microphone. So I've set that up, and I guess from now on, this is the microphone that I will be using to make future videos. So, concerning the request for science people to give me feedback, please watch this video and you'll understand why I am making that suggestion. A few days ago, after hearing for the umpteenth time that flat earthers now think that it's entirely possible to see a 24-hour sun in Antarctica, they are using excuses like a sun simulator, which is just some glorified fancy device. If you really look into it, all it's doing is it's producing a light spectrum that matches the frequency spectrum of our sun. And that's it. It has nothing to do with brightness. It has nothing to do with lighting up an area. It really is about producing light that matches the frequency spectrum of the sun. However, flat earthers in their natural style have taken that and have decided to use that as some form of get out of jail free card to now claim that they, the nameless faceless they, are going to trot this out and use that to somehow fool the final experiment expedition into thinking that they really are seeing a 24-hour sun. Some of them have proposed other solutions like multiple suns, and that as one is suddenly going out of view, the next one is suddenly going into view, and how that works and how people can't see the transition. That is an entirely different debate, but I was just going to focus on the technological side of things. So there are flat earthers such as Flatzoid who have said that they were going to put some kind of solar simulator device on some form of balloon and kind of waft that thing around the expedition so that they could then be fooled into saying, there, see, we've got a 24-hour sun. If this is a technological solution to a problem, we should be able to use well-known technology that every one of us have probably handled several dozen times in our lives already for comparison. And I decided to focus on a 100-watt light bulb. I made this spreadsheet available. Check the description. And in that spreadsheet, I've also put several references as to why I chose some of these numbers. But from what I can tell, a 100-watt light bulb has the equivalent of about 1,600 lumens thereabouts. There are sites that have told me that a lumen is a measure of watts per square meter, and lux is also involved in that too. I just eyeballed the average size of a standard incandescent light bulb, and I put it at about roughly 2 inches in diameter. 1 inch is 25.4 millimeters. 4 times pi times the radius squared. That should give me the surface area of that light bulb. And I get the light bulb's surface of 0.007854 square meters. If a light bulb puts out 1,600 watts of light in that amount of space, then if I divide 1,600 by the surface area, theoretically, the surface area should be the equivalent of 12.57 watts per square meter. If I were to divide one by the other and pretend that the surface area of that light bulb was in fact 1 full square meter to match the same brightness, it should be the equivalent of 203,000 watts. This section calculates how big an artificial light should be. We know that the sun has an angular size and that no matter where we are, that angular size should be 0.53 degrees. Using a bit of math, for some distance that we put in and the angular size, we can calculate the radius of that light source, assuming that that light source has the equivalent of a two-dimensional disk directly facing us. According to various resources online, the sun should put out about 1,350 watts per square meter at the Earth's distance from the sun. It has to go through the atmosphere, and from what I can tell, the atmosphere will absorb some of that energy, and that if the sun was directly overhead on a cloudless day, the best effort would be about the equivalent of 1,120 watts per square meter. So there is going to be some sort of atmospheric absorption. Flat earthers have used the inverse square law in the past to discredit the moon's brightness when the astronauts were on it. For some reason, flat earthers think that it should be so bright that the astronauts would burn up on the moon's surface in nanoseconds or thereabouts. So using the same inverse square law that they like to talk about, I use that to calculate how many watts per square meter the sun should be for any given distance. And that inverse square law pretty much makes this constant at 52,000 watts per square meter. For example, the 100 watt light bulb at a distance of 5.4 meters away from the observer means that the light bulb should be that big in square meters, and it should have 207,000 watts of radiative energy per square meter, which kind of matches this. So now we get to ask some very interesting questions, such as if they are going to use a sun simulator and light up the area to fool the final experiment expedition, how far away do they have to be for the lie to be believable? Obviously, a 100 watt light bulb 5.4 meters away is going to be very easy to detect, so it has to be a much bigger light source further away. Half a kilometer? This section calculates how many 100 watt light bulbs should theoretically be required to produce the same amount of light when that light source is half a kilometer away. And according to the math, and I've actually done this in two different ways, both of them seem to agree, I would need the equivalent of 8,500 light bulbs of 100 watts, or their equivalent, such as LED lights. That's this row here. The next row is the watts required if it was an LED. Again, you can find resources online. A 100 watt equivalent light bulb should theoretically draw about 18 watts of electricity. So if you multiply the number of light bulbs by each light bulb's electrical demand, if said light was half a kilometer away, you would need a power supply capable of putting out 154 kilowatts continuously. Assuming a 120 volt system, that should be about 1,283 amps. And just for the fun of it, at least here in North America, house wiring is 14 gauge, which has a 15 amp carrying capacity, theoretically, which I believe one of the brands you can buy at the hardware store is Romex NMD90. You can look that up. So you would need 85 separate wires just to light this contraption from said power source. Of course, we have some fairly powerful zoom lenses and optical devices, though half a kilometer away may not quite be enough. So let's go 1 kilometer. They might be able to fake it at 1 kilometer. And at 1 kilometer, according to my math, I suspect they would need the equivalent of 34,000 100 watt light bulbs and a power source capable of putting out over 5,000 amps at 120 volts. And just in case 1 kilometer is just not quite far enough, let's say they extend that out to 2 kilometers. Now you need 136,000 light bulbs or 2.4 megawatts. Let's just say, for argument's sake, that they're able to pull that off. Let's just say that they can use some form of portable power source capable of putting out 2.5 megawatts and move this thing in a 2 kilometer radius around the expedition. What happens if they stray away from this 2 kilometer distance? So down over here, I assume a fixed size and brightness of a light source. Using the same inverse square law, I would then calculate the difference between the intensity of this sun simulator at 2 kilometers versus the equivalent intensity at 2.5 kilometers, for example, or you could go 2.2 kilometers. You can see how these numbers change. So remember, in order to fool the final experiment expedition, they have to maintain a constant distance. They have to maintain a constant light intensity. And to add to it, the final experiment expedition can also check the color spectrum of this light. LED lights have a very narrow band of wavelengths that it outputs. They're getting much better with the technology, which is a more broad spectrum. I don't know yet if there are any LED lights that put out the full light spectrum or if it is in several very narrow bands so that our eyes perceive it as a full spectrum light or not. So that brings me to several experiments that the expedition can do and hopefully make the final experiment that much better. When they get down there, will the sun maintain the same brightness? I'm going to put a link to a video that I made a long time ago where I tried to measure the sun's relative brightness throughout the day. The expedition could do something very simple and crude like what I did, or they can get a much more refined and well-defined device for doing that. The second test that the final experiment crew can do is to measure the light frequency spectrum, and that could be done, for example, if they were to get a food container, spray paint the inside with a matte black paint, drill a hole in the side and stick on a prism so that the light entering goes through that prism. The prism splits the light out into different frequency bands, and then they can have a small web camera or GoPro or something like that inside so that it can see what the spectrum looks like on a silver screen on the other side, for example. So there's a very simple device that they can build to create a light frequency spectrum measuring device. And then the last experiment that they can do is to see whether or not the sun changes size physically. If the sun maintains a precise angular size of 0.53 degrees for the entire 24 hours, that would mean that whatever the light source was, it would have to have maintained the same distance as it circled around them. In contrast, if the Earth is flat, and if they are south of the Tropic of Capricorn, and that the sun just goes back and forth from east to west and then back to east in the 24 hours, the law of perspective says that not only should the sun itself change in angular size, but that also with the inverse square law, it should also get brighter and dimmer as a result. And so that's where the rest of this spreadsheet comes in. For every degree of zenith angle an object like a star changes, it's well known that we travel 111 kilometers or thereabouts on the surface of the Earth. I put them at a local latitude of 79.5 degrees south, and using a straight bit of simple math, I compute an XY coordinate where they should be, and the actual angle itself doesn't really matter. So I put them at the equivalent of 90 degrees south or straight down from the North Pole. so that their x-coordinate is 0, but their y-coordinate is the full distance from the North Pole. Again, how high is the sun? No flat earther gives us a valid response. So once again, assuming a 45-degree angle to the sun and a known distance from the observer to the GP of that many kilometers away, the sun should theoretically be that high above the Earth. Using 0.53 degrees at a 45-degree angle, the radius of the sun should be about that. This is the same number that I got from over here. And for some arbitrary light source of this radius, it should have that many square meters. With all of these, I was then able to calculate where the sun's GP should be, more or less. I'm just using the hour angle, which is pretty much fairly similar. Using these two, I then calculate the x and the y coordinates on a flat Earth, and then I calculate the sun's distance, and with that I use the inverse square law to calculate what the sun's intensity should be measurable at their location at that time, and it produced this graph over here. So now I'm going to come back to my request for feedback and request for help from the sciencey type people. I would very much appreciate if you guys could look at my math and tell me where I made mistakes. I'm sure that I made them all over the place. I do also know that I made a lot of assumptions. For example, a 100-watt light bulb may not produce 1,600 lumens of visible light. In fact, it might be more like 1,000 or 700 lumens of visible light, the rest of it being in near infrared, or in the case of an incandescent light bulb, probably even in the far infrared. That number alone would skew all of these results, and I get that. For the most part, I think that my math is correct. All the sun various goodness found on the Wikipedia site says that the Earth is 149.6 million kilometers from the sun. So if I put 149,600, according to the same math, it should be 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3 is 24, 25, 26. It should be 1.5 times 10 to the 26. This is, of course, only looking at a hemisphere, or the amount of light that the observer can see. You have to multiply that number by 2 to get the total radiative energy, which happens to be 3.8 times 10 to the 26 watts in luminosity. I think I've done the math correctly, but as always, somebody else checking the math is very appreciated. I would also invite others, if this has inspired you to think of something else, feel free to make your own video on this subject. Quite honestly, this video was only baked in about 48 hours. I'm now recording this on Friday afternoon, or at this point, Friday evening. I only got this idea on Wednesday. Last night, I worked on this spreadsheet, and tonight I'm making this video. That's going to be it for now. Thank you for watching. If you like the video, you know what to do. With that, I'm going to see you again in another video soon enough. So bye for now.